In experiments have been carried out where these 20 giga electron volt electrons are aimed at a hydrogen target, which consists of protons. Suggest with a reason what happened to the path of these electrons. Yeah, the term relativistic means closer to speed of light. It's not like same as speed of light, but yes, it is closer to speed of light. So what will happen if we have this 20 giga electron volt electron? So at a very high energy, the wavelength which is associated with this electron, as we worked out in the last part, that the wavelength associated was a very low. It was about 6.2 into 10 power negative 17 meter, which is a very low value. And it is approximately, so as a result, what will happen when it passes through, and the order of the nucleus, like the nucleus of an atom, is also in the range of a femtometer 10 power minus 15 meter. And the electron is not behaving like a particle, electron is behaving like a wave. So as a result, when a wave passes through a gap, what will happen? It will diffract. So we'll observe a diffraction pattern. Like if I draw the wave fronts, so these are the wave fronts, and this is a gap. The nucleus is there, like the dimension of the nucleus. So when it passes through the gap, it will spread or diffract. So how we score 2 marks here? We'll mention electron is behaving like a wave, because as the gap size is approximately equals to the wavelength associated with the electron and moving at this relativistic speed, so it will diffract. Is it clear? So particle can behave like a wave can behave like a particle. Question 16. The photograph shows a circular tunnel in a large hadron collider, which is underground particle accelerator. The circumference of a tunnel is 27 kilometers. In a Large Hadron Collider, a magnetic field allows the charged particle to move at a constant speed in a horizontal circular path of a required radius. By reference to the forces acting on the charged particle, explain how this is achieved. First thing, whenever you want to move something in a circular path, the force should direct towards the center. And if the force is directing towards the center, whenever we want a particle to deflect in a magnetic field, the direction of the motion and the direction of a magnetic field should be perpendicular to each other, like 90-degree. So the magnetic field is into and the particle is moving in this way. So as a result, what we'll observe the particle will deflect. So whenever we want a deviation or deflection of the particle, we should always apply a magnetic field which is perpendicular, 90-degree. So here, the first point is the magnetic field should be perpendicular to the direction of the motion. And as a result, the magnetic field will direct toward the center, which will act as a centripetal force, which will cause a deviation or a deflection. That is 2 points. Then the second thing is the force on the charge in a magnetic field. So whenever a particle is there in a magnetic field, force on a charged particle is QVB. That is a magnetic force. And whenever object move in a circular path, the centripetal force is mv square over r. Because the magnetic field is causing a circular motion, so we can say the magnetic force will be equal to centripetal force. So magnetic force is QVB and the centripetal force is mv square over r. So square will cancel with this v. So we can say QB is equals to mv over r. So this is a formula which will relate the radius, magnetic field, mass, speed, and the charge of the particle. So we'll mention this point like relating, or if we need the radius, so radius will be mv over qb. B stands for the strength of a magnetic field. So if we apply a stronger magnetic field, the radius will decrease. If V is the speed, if a particle is moving at a high speed, it will have a greater radius. M is the mass of a particle. Actually, it's not only mass, it's mass to charge ratio. So if a particle is having greater mass to charge ratio, less deflection because greater radii. The particle is having smaller mass to charge ratio, more deflection, smaller radii. So the points you score, one is particle has to move in a circular path, the force should direct toward the center. The magnetic field should act perpendicular to direction of motion, which create a centripetal force. And the centripetal force, the magnetic force equals to centripetal force. And then the last part, you will write this formula. In part B, in practice, the Large Hadron Collider uses electric field to accelerate the particles so their momentum gradually increases. State and explain how the magnetic field in LHC must change as the momentum of a particle increases. So if the momentum of we just derive a formula that R was equals to mv divided by qb. That was a formula we just derived. So the question is, if a particle accelerating, if the speed of a particle is, if we want a constant radii, because in the Large Hadron Collider, the radius is 27 kilometer. As you mentioned here, sorry, circumference, not radius, circumference. The circumference is 27 kilometer, means the total circular length. But it is accelerated in a section. Means the speed of a particle in this section will be different for speed of particle in this section. Speed will be different in all these sections. So the question is how the magnetic field should change so that we keep this particle rotating in a same order. We want to keep the radius same. Otherwise, if the radius changes, the particle may leave the track, may leave the tunnel. So we want to rotate this particle in a tunnel continuously. So what we should do, if the speed is increased, we have the formula R equals to mb divided by qb. So if I want b, the relation of b is equals to mb divided by qr. M is a mass of a particle. It won't change unless it will move at a relativistic speed. Q is the charge of a particle. That's not changing. R, we want to keep it same. So what is happening here if the velocity is increasing? So what we should do, we should apply a stronger magnetic field. So section of this tunnel, section of this Large Hadron Collider, we will use different magnetic fields, and each section, the magnetic field will increase so that it will continue to rotate in a same radius. Is it clear?
Yes, sir.
So we have to increase the magnetic field so that it will move in a same radius. Collision between the particles in high energy physics experiments often result in the production of electron-positron pair. Calculate the minimum energy in joules required to produce electron-positron. If I want to produce electron and I want to produce a positron, what is the minimum energy needed? So we have the formula E is equals to mc square. I want to produce two masses. The mass of an electron and positron is same as their antiparticle. So that is 9.11 exponent minus 31 kg. But I want to produce two of them, so this should be multiplied by 2. And then the speed of a light, so it will be 3 into 10 to the power 8 square. So I will know how much energy I need, minimum energy I need to produce these. So 9.11 exponent minus 31 times 2. Why times 2? Because I want to produce electron and a positron. So that's why it should be times 2. So it will be 1.64 into 10 to the power minus 13 joules. That's the energy which we need to produce them. By converting your minimum energy into mega electron volt, give the rest mass of electron in mega electron volt per c square. So this is the energy which we need to produce two of them. So how much energy we need to produce one of them? So we'll just calculate the total energy we need, and at the last we'll divide by 2. So we'll know how. So this answer was 1.64 into 10 to the power minus 13 joules. Now what we do, we will convert this energy. Now as you can see, we want to convert into mega electron volt. So minimum energy in mega electron volt, and energy in mega electron volt is same as mass in mega electron volt per c square. So what I will do, I'll just try to convert this first joules into electron volt and then electron volt into mega electron volt. That is what we want to do. So if I want to convert the joule into electron volt, what we'll do, because we know one electron volt is equals to 1.6 into 10 to the power minus 19 joules. So if I have this much joules, like 1.64 into 10 to the power minus 19, 1.64 into 10 to the power minus 19, so this will be x cross multiply. So actually what we do, we divide it by 1.6 into 10 to the power minus 19. So when we divide this value, 1.64 exponent minus 13, not 19, 13. This was 13, that's why. So this also 13. So divide by 1.6 exponent minus 19. What's the answer here? What's the answer here?
Oh, 1.025 by 10 to the power negative 32.
We have to divide.
Yeah, so 1.64 by 10 to the power negative 13 divided by 1.6 by 10 to the power negative 19. 1 by 10 to the power negative 32.
I don't think so, because see, it is 1.64 into 10 to the power minus 13 divided by 1.6 into 10 to the power minus 19. So this power will go there in numerator, so it will become
Oh
plus
yeah,
9,
yeah. It's 1 by 10 to the power 6.
6. And then electron volt, I want to convert into electron volt is there. This was 1.02. So I'll write the three significant figure 1.02. This electron volt I want to convert into mega electron volt. So I will divide it divided by 10 raised to the power 6. Because electron volt, when mega electron volt to electron volt, we were multiplying. Now we'll
Yeah.
divide, so we'll get 1.02. 1.025, yeah. 1.025 mega electron volt is the energy. But that is the energy to produce electron and positron. But if to produce only electron, I need half of it. So if I need half, so it will be 0.51 mega electron volt. So 0.51 mega electron volt energy. And remember, energy in mega electron volt is same as mass in mega electron volt per c square. So we need 0.51 mega electron volt per c square. So to produce one particle, I need this much amount of energy. Is it clear?
Yes, sir.
Okay. Next, we have question 17. The diagram shows a track of a charged particle in a magnetic field. The field is at right angle or a perpendicular and to the plane of, and its direction is out. So magnetic field is pointing out. AB is a thin sheet of a lead, as you can see. First, work out the direction of a movement of particle. First, when looking at this, which direction the particle is moving? Is it from P to Q or Q to P? So how we identify? Look, when the particle passes through this thin sheet, it will lose some energy. So when it loses some energy, the deflection will be, because it has less energy, so it will deviate or deflect more. So first we conclude that the particle is actually moving from P to Q. Why not from Q to P? Because if it was moving from Q to P, then what should happen? It should deflect, like it should lose energy when passing through this lead sheet. It lose energy, so it will deflect more. But it is not deflecting more. It is not deflecting more. So it shows that the particle is moving. As a particle loses energy, let's say the particle was moving in a magnetic field like this. And if I place a thin sheet and the particle loses some energy because of this thin sheet, so what will happen to deviation of the particle? It will, because it has lost energy, so as a result, it will deflect more. So same thing when you see here, Moving from P to Q, it has deflected more. So first, what we concluded? We concluded that the particle is actually traveling from P to Q. Why it is traveling from P to Q? Because the Q is having the curvature of a Q is greater than P, or it shows that the Q is slower than P. Why less energy, more? Because the deflection depends on the momentum as well. The deflection in a magnetic field depends on the momentum of the particle. No, 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 no. The mass to charge ratio does not change because the particle is not, the mass to charge ratio does not change. We have the formula that R is equals to mv divided by qb. That is the formula in a magnetic field. So q is not changing, m is not changing, b is not changing. But when it loses energy, v decreases. So if that v decreases, the radius will also decrease. That's why. Now, which particle is this? Is it a positive particle or a negative particle? So how we work out that? So again, what we have to do, we have to use they already mentioned the magnetic field is out. So magnetic field is out. So if I consider this as a positive particle, we don't know, but we consider it's a positive. So my index finger should point out. I'm using a left hand because I consider as a positive. And the direction of the force is in this way. Because the direction toward the center. Index finger is pointing out. My second finger represents the direction of the particle. My index finger is pointing towards me. My second finger is pointing the direction of the particle. So if it was a positive particle, then what should be the track? It should go like this. So because it is not following the left hand rule, so it means this is not a positive particle, it is a negative particle. And how I can confirm? If I apply a right hand rule, my index finger is pointing out, means towards me. My second finger is pointing in the direction in which the particle is moving. So you can see my thumb is pointing in the direction of the force. So if it was a positive particle, it should follow a left hand, but it is not following a left hand. So this gives an idea that this is a negative charge particle. Is it clear? So how we write the answer here, like the points we'll include in our explanation. First thing we'll mention, a particle is moving in a magnetic field perpendicular to the magnetic field. So it loses energy. So its curvature will increase, like deflect more, or Q is having a smaller area than P. So particle has lost some energy. And the magnetic field is perpendicular. If it was a positive particle, it should deflect downward, but it is going upward. It shows that this is a negative particle. Is it clear? Question 17.
Yes.